Just as we envision the Earth having two poles and a magnet having two poles of opposite polarity, of opposite charge, covalent bonds that share electrons but share them unequally can also be described as being polar. And so that then would translate into polarity of the entire molecule, considering a couple of other things. But a polar molecule would be one that seemingly one part or one end of the molecule tends to have a positive charge while another end seemingly has a negative charge. Now this is important because this can be used to help explain why different substances that otherwise might be fairly similar in terms of weight, mass, can display different characteristics and different strengths of bonds between them. And different properties such as your melting and boiling points, why there is such a wide variance. And it all stems back to the bonding that occurs within the molecules themselves between groups of two atoms within that molecule. So this idea of polarity stems from the fact that when we compare elements and we determine what kind of bond it is, we look at their electronegativities. And all the elements have different electronegativities. So in a covalent bond, and this would be one that's formed when you have a small difference in electronegativities, or a relatively small difference, the electrons are being shared, but in most cases they're being shared unequally. The only case in which you would have perfect equality in the sharing of the electrons would be, for instance, with your diatomic elements, where the two atoms are the same exact element and they are bonded to each other, in which case your electronegativity difference is 0, and that indicates that you have equality in sharing. But any other covalent bond, there is going to be, to some degree, some inequality in that sharing. The more electronegative element is going to be attracting the electrons more, and so that end of the bond is going to have more of a negative type characteristic, a negative charge type characteristic to it, because the electrons are favoring that end of the bond. So if we consider a bond like this, like that which we see in water, we consider one of the hydrogen-oxygen bonds. Oxygen has an electronegativity value of 3.50, hydrogen 2.20. Obviously, oxygen is the more electronegative element, so it is going to attract the electrons more. And so the electrons that are in that bond are going to favor the oxygen end of the molecule, or the oxygen end of the bond, rather. And so that end will seemingly have more of a negative charge to it. And it's not a full-blown negative charge because it hasn't totally removed the valence electron from hydrogen, so we refer to it as a partial negative charge. And we use the lowercase Greek letter delta to represent partial. So delta minus is our partial negative charge. The less electronegative atom, in this case hydrogen, is having the electron drawn away from it, so it's the positive nature of its nucleus and its proton are more exposed, and therefore that end of the bond takes on more of a positive type appearance in terms of its charge. But again, it still has some of that electron density in that bond, and so it's not a full-blown positive charge, but yet we call it a partial positive charge. And so assigning those to our diagram here, the electrons are being withdrawn towards the oxygen end of the bond, therefore oxygen takes on a partial negative charge, and hydrogen would be designated with a partial positive charge. This kind of bond, because it still represents a sharing of electrons, is covalent, but because we see the appearance of opposite charges on opposite ends of the bond, this is referred to as a polar covalent bond. So just because a molecule contains polar bonds, does that necessarily make that molecule polar? You have to ask yourself two questions and consider a couple of different things. First of all, you can't have a polar molecule unless, yes, there are polar bonds present. So that's a given. If your bonds aren't polar, then there's no way the molecule is going to be polar. But once you get past that question, if, yes, you do have polar bonds, then you need to look at the molecular shape. And you need to look at the orientation of those polarities and the polar bonds. And does the geometry of the entire molecule arrange those polarities such that they would cancel each other out? So you almost have to think in terms of vector quantities and would they balance out. If yes, there are polar bonds in the molecule, but no, the shape does not cause the polarity of those bonds to cancel each other out, then your molecule as a whole, one portion will appear to have a negative charge, the other will tend to have a positive charge, and thus we would refer to the molecule as a polar molecule. But if you answer yes to both, yes, there are polar bonds, and yes, the molecular shape does cause the polarities to cancel each other out, then we refer to the molecule as a whole as being nonpolar. So you need to be able to make the distinction between polar bonds and polar molecules. It is possible to have a substance that does have a large degree of polarity in the individual bonds, but yet overall as a whole molecule illustrates nonpolarity because of the way those polar bonds are arranged in three-dimensional space. So with polar molecules, these display two poles, a positive end and a negative end. Another word that we use for this in kind of a shortened form is the term dipole. Di for two, pole indicating the polarity. Now how this impacts the characteristics and the properties of our molecules, if you have a large electronegativity difference, but yet it's still being shared, you have a large polarity. So it's almost as if the bond is an ionic bond, but not quite. Well, the larger the polarity is, the stronger the attractive forces, the intermolecular forces, are going to be. And the stronger those forces are, the more energy it's going to take to cause those adjacent particles to let loose from one another, such as what we need in the melting process or in the boiling process, to coax those adjacent molecules to have greater freedom of movement from one another and transition from the solid to the liquid state at the melting point, and from the liquid to the gaseous state at the boiling point. So the stronger the polarity, the larger the polarity, the stronger the intermolecular forces, and the stronger those forces are, the higher melting point and boiling point temperatures we're going to see for a particular substance.